Hey class. In this video, we're going to begin chapter 2. I'm going to give a little bit of an intro and then go over section 2.2. So if there was any lesson to take from the videos on chapter 1, where we talked about what differential equations are to begin with, it is that differential equations are hard to solve. And if we expect to solve them, we probably have to get lucky in some way. And that's basically the gist of the next bunch of sections and chapters is that we're going to look for ways that we might get lucky with the differential equation. So we're going to break down into a number of different special cases where we can solve and can find solutions, and hope that that sort of covers most of the differential equations that we'll see in real life. So the first way that we're going to break this down for chapter 2 is to only consider first order differential equations. And the sort of general form of that is written here in black, where we only have one order derivative, only a first derivative. And we're going to assume that we can get it by itself on the left-hand side of the equation. And then everything else on the right is just going to be some function of x's and y's, but not a function of other derivatives. And then the other thing we have is the initial condition right here. So this is an initial condition. And if we have this, if we have the differential equation and an initial condition, that makes this an initial value problem. So it tells you 1 point on the solution, y at a particular value of x, x naught, equals a particular value of y, y naught. And we used that in the direction fields, where if we knew 1 point on the solution, then we could guess the shape of the rest of it. So that's why that's some intuition about why an initial value is important. Anyway, even though we've already simplified this down to first order and making it so that we can get the derivative on all by itself, we still don't necessarily, it's not necessarily obvious how to solve this. So we can take an even simpler case and assume that the right-hand side only has x's in it. Okay, so let's say dy dx equals some function g that's just of x. Now this looks like something that you've seen in calculus, and you can solve it. You can solve by anti-derivatives. So we just integrate, right? So we get integral dy dx equals the integral of g of x. And of course, we want to integrate with respect to x, and we know that we're going to get a plus a constant. So this quantity right here is the anti-derivative of g of x. An alternative way to think about this, if you want to use that initial condition, is by using the fundamental theorem of calculus. So in that case, fundamental theorem, remember there's like two parts of it. And if you go look at the statement of it, you get that y of x minus y at a particular point, which at this point we're going to use our initial condition. So that difference equals the derivative, or the integral from your initial x value to an arbitrary x of y prime of some other variable of integration, tau, y prime of tau d tau, which we can rewrite because of our differential equation. We know that this equals the integral x naught to x of g of tau d tau. Okay, so this right here is the fundamental theorem of calculus, which again, the statement that you sort of use less often in calculus but is an important part of it is that this function where the integral or where the variable is one of your limits of integration, um, that of this integral of the derivative is just that you can evaluate that by taking the difference of the antiderivative evaluated at those 2 points. Okay, and then this part here is because of the ODE. Okay, this ODE up here. And now if we take this equation, we have as a consequence that y of x, which is the thing we were looking for, equals, I'm going to add the initial condition to the other side. So we have y naught is equal to y of x naught plus the integral from x naught to x of g of tau d tau. So this is essentially the same thing that we got up here, where we have our solution, which I didn't really write in, but our y of x equals, those kind of cancel each other out. Y of x equals antiderivative of g plus a constant. And then same thing down here. We have y of x equals the antiderivative of g, what you get by just integrating it, plus a constant. And if we know our initial condition, that actually tells us explicitly what the constant is. So that's nice. And I mean, very early, like in chapter 1, and if you go back to the book, the very first example is f equal of a differential equation is f equals ma, and we solve that just by taking antiderivatives of that derivative, that second derivative acceleration a, and you can just take an antiderivative and get back to your position function, and that's how you solve it. And so we saw very early on that you can solve differential equations if they're simple enough, and that's exactly what we have here. We have a simple enough type of equation that we know how to solve. So that's a good place to start. Now, can we do a little bit better than that? Can we find something that's slightly more complicated than only having x's on the right-hand side? So the answer is yes, we can consider a slightly more complicated form, and that is section 2.2 on separable equations. So a separable equation is what I have written out here, and we have in this case, we took the general equation that I wrote at the very beginning of the video, where we have our derivative, our first derivative equals some function of x and y. And the special case is if you can break it off into a product of something with only x's, this g has only x's in it, and then the p has only y's in it. If you can write your right-hand side, your f of x, in this form, then you have a separable equation. And I'm calling this equation S. That's what this is here for. I'm going to refer to it later. And the intuition of why maybe this is something that we can solve for is that in the previous example, if we had the right-hand side with only x's in it, then we were good to go. So let's rewrite this. Setting. I'm going to define a new function, h of y, which is going to be equal to 1 over p of y. And that's because I'm going to divide by my p of y to get all the x's by itself. And so what I have in this case is h of y dy dx equals g of x. So this is nice because on the left-hand side, we really just have y's. We have h of y and then y prime. And on the right-hand side, we have our g of x, just x's. So it seems like we should be in good shape for taking antiderivatives or for integrating. So let's suppose we can take antiderivatives of our functions h and g. So let's say capital H prime of y equals little h of y, and big G prime of x equals little g of x are, so suppose these big h and g functions are antiderivatives. Then we can rewrite our equation to look like h prime of y times dy dx equals big G prime of x. But this sneaky thing is here that on the left-hand side, we have a derivative, that h prime with respect to y, and on the right-hand side, we have a derivative with respect to x, which is kind of annoying. But we can make the observation that the left-hand side is actually an expression of chain rule. If we think about how big H is a composite function, it's a function of y, which is itself a function of x. So we can rewrite the left-hand side as d dx of h, which is a function of y, which is a function of x. And then on the right-hand side, we still have, well, I'll write it this way, d dx of big G of x. That's just another way to write big G prime. So let me clarify. So this equals G prime of x, just a rewrite. And then this part here is chain rule. Okay, so go from the bottom to the top. Think about it. Think about what it would have to be. So d dx of this composite function here is the derivative of h with respect to y first. So remember, you keep the inside stuff the same. And then you multiply, and that gives you your h prime of y. And then you multiply that by the derivative of the inside, right? So the dy dx is the derivative of the inside. So work that out for yourself, write it out if that doesn't make sense to you, because that's a pretty important concept. So what we have now is actually really nice because they both start off with a d dx. So the derivative of both these functions, both the h function and the g function, are the same. So that means that the functions must differ only by a constant. Okay, so that means that h of y of x is going to be the same thing as g of x, except for maybe plus a constant. And we're essentially done. This gives us an implicit solution for what we're looking for, which is y, for y of x. And maybe, if we're lucky, depending on what this thing looks like, maybe we can solve for y of x. It would just depend on the problem. We'll see when we do examples. Okay, so let's summarize. If you see an equation and you determine that it's separable, so it has the form S that we saw earlier, what do? Step one, write it in the form so that you can see very clearly that it's separable. So separate the equation to identify the p of y and g of x that were up in, up here in this equation S. So we need to find the g of x and the p of y. Step two, remember we divided by p and then found an antiderivative. So we need to find antiderivative, find an antiderivative, which we will call h of 1 over p. when we divided p. So i.e. h prime of y equals 1 over p of y. And that may or may not be easy, but hopefully it's easy. We needed another antiderivative, so find an antiderivative big G of little g, that is, big G prime of x equals little g of x. And then we plug into the solution that we got before. So there was our solution. Let's see. So then the implicit solution is h of y of x, since we found big H, equals big G of x plus a constant. And then our last step is 5, if possible, find y of x explicitly by solving the implicit equation for y. So if you can do that, then you can get y of x equals blah, blah, blah. And that's your answer. Okay, so that is, wow, now we have a recipe, an algorithm for actually solving one type of equation, which is really nice. It's not that many steps, but it's kind of a few things to memorize. And there's actually a little shortcut to thinking about this. So let's look at our shortcut. Let's take our equation dy dx equals p of y times g of x. So what I'm going to do here, I did in a previous example, and it looks wrong. It looks like nothing to do. And I will just go ahead and tell you that this is backed up by some actual mathematics that is a bit outside of the scope of the class. And so trust that it is actually an okay thing to do mathematically. If you don't want to trust that, or for whatever reason you are still unhappy with this, just think about this as a shortcut to remembering how you solve these equations. Okay, so what I'm going to do is multiply by dx. Okay, so dx, in the way that you have learned calculus, is not an actual quantity that you can multiply by. But again, there is some mathematics that allows you to like treat it as a quantity. We're going to do it anyway. And then we get dy equals p of y, g of x dx. Let's get the y's on the other side. So then we get 1 over p of y dy equals g of x dx. Now we've got a dy on one side and only y's on one side and only x's on the other side. And these dy's and dx's make us think that we can integrate. So let's just put an integral sign. And these integrals make a lot of sense. This one on the left-hand side is an integral with respect to y. And the one on the right-hand side is an integral with respect to x. So this reminds you that you can find antiderivatives. So now we find a h of y, or antiderivative of 1 over p, and y is a function of x. And on the right-hand side, we take an antiderivative and get our g of x, and then we always remember that we have to add a constant. So that's just sort of the shortcut reminder for how to do this. These are actually pretty simple. The hard thing is finding the antiderivative, but usually if you're given a homework problem or an exam problem that's asking you to find an antiderivative, it's going to be something fairly straightforward that you would have learned in calculus. All right, so the last thing in this video, I'm just going to do one example. We'll do more examples in class. There's lots of examples in the book. You'll do lots of examples in your homework. This is the sort of thing where it just more practice will reinforce the concept a little bit. So here's our example problem: dy dx equals x minus 5 over y squared. And I'm going to point out here that this is non-linear. It's non-linear because it's got some crazy things happening in the y's. We don't have just like straight y's or multiples y times things. If you go back to section 1 and think about what the definition of nonlinear is, or linear, then you'll see that this is a nonlinear equation because of that y squared in the denominator. So normally nonlinear is hard and you don't know how to solve it, but because this has the special case of this of being a separable equation, it is nonlinear. So is it actually separable? Yes, it is. And if you want to see this really explicitly, we can write it out. We've got the dy dx on the left-hand side like we want. And on the right-hand side, we can write it as 1 over y squared. So that's our p of y and our x minus 5. So this is separable. And this is our, what do I call it, p of y. And this is our g of x. So we have a separable equation. So now we can do our little shortcut and we can get all the y's on one side, all the x's on the other side. And so this is pretty easy. We get a y squared dy equals x minus 5 dx. And then we can integrate. These are reasonably straightforward antiderivatives to do. So next we do our antiderivative. And we get 1/3 y cubed equals 1/2 x squared minus 5x plus c. Now, when you do antiderivatives, normally you would have a constant on both sides, right? But we could always just like subtract the constant over. So that's why I only have a constant on one side. So we have an implicit solution here because y isn't by itself, but I could solve for y by itself pretty easily. And I would just get y equals, just brute force this and multiply everything over by 3 and then take the cube root. So we get 3/2 x squared minus 15x plus 3c cubed root. And we could replace this with c again. We could just write c because it's an arbitrary constant. C doesn't matter if it's c or 3c, but you're never going to get marked off for having a 3c instead of a c. There's not really a correct way to do that. So anyway, that is our solution, and that's how you solve separable equations. In the next section, the next two sections really, we're going to talk about special about ways to solve two other special types of first order equations. So we'll see you then.